How do solvents affect nucleophilicity in chemical reactions? Let's find out. Nucleophilicity, or the ability of a species to donate electrons and do a nucleophilic attack, is not an inherent property. It's highly context dependent. In particular, the solvent we use can affect the nucleophilicity of molecules. Solvents that dissolve nucleophiles can broadly be classified as polar protic solvents or polar aprotic solvents. They both have polar bonds present, but polar protic solvents also have hydrogens, aka protons, available to participate in hydrogen bonding. That is, they have hydrogens attached to highly electronegative atoms like nitrogen and oxygen. Polar aprotic solvents will have some other polar bond like a carbonyl, nitrile, or sulfoxide group. They may have hydrogens, but they won't be able to participate in hydrogen bonding. To see how the solvents affect nucleophilicity, let's look at two extremes of our halogens, fluorine and iodine. Specifically, they're ions so that they dissolve in our polar solvents. The fluoride ion is very small, almost half the size of iodine. This does two things. First, the -1 charge is less spread out on fluoride. This higher electron density means it has a higher local charge, which causes it to more tightly bind to the water through hydrogen bonding. Its small size also causes it to be physically trapped by the solvent molecules as well. This means that if fluoride is trying to participate in a reaction, the water, or other polar protic solvent, gets in the way and slows down the rate of reaction. On the other hand, the much larger iodide ion is able to spread that -1 charge out over a much larger area. This lower electron density means the solvent molecules are only weakly attached to it. The larger size also makes it harder for the solvent molecules, like water, to physically block it. This means if iodine is trying to participate in a reaction, water, or other polar protic solvents, don't affect the rate of the reaction as much because they can't hold the iodide back very well. So, in a polar protic solvent, reactivity, or nucleophilicity, will trend with size and increase down the periodic table. Now let's look at our aprotic solvents. A polar aprotic solvent can't interact with either ion very well. They only have a negative charge available on the dipole because the positive charge is buried in the center of the molecule and blocked from interacting with anything else. The iodine didn't really interact with the water molecule or polar protic solvents anyway, so the lack of hydrogen bonding in the aprotic solvent doesn't make much of a difference to its reactivity. The lack of interaction, though, makes a big difference for the fluoride ion. Without the attraction of a hydrogen bond, fluoride is no longer trapped by the solvent, freeing it to react, which it will do very strongly. This dramatic change for fluoride, coupled with the less dramatic change for iodide, causes the trend for nucleophilicity to reverse in aprotic solvents. That is, nucleophilicity will increase up the periodic table. What about left to right on the periodic table? Well, within a row, the atomic radii do not change so dramatically, so the solvent has little effect on their nucleophilicity. In this case, nucleophilicity follows our usual rules for both solvents. That is, the less electronegative the atom, the better able it is to donate its electrons in an attack, and the better nucleophile it will be. So, nucleophilicity increases right to left on the periodic table. Putting this all together, we get the following trends. Nucleophilicity in protic solvents increases down and to the left on the periodic table. It follows our typical trend that decreasing electronegativity increases nucleophilicity. But in aprotic solvents, the trend flips in our columns, so nucleophilicity increases up and to the left instead. And that's how solvents affect our nucleophilicity.